Do I have voice? I have voice. Unbelievable. Okay, I'm not even going to talk a lot. I just already have code here. It turns out not to be very fast. So I'm going to redo it. I'm going to start from scratch. So let's say blop blop was price 4. Code IO stream type. Good. Well, I need a class. I'm going to call it the same as in the previous one, which was prime bound cofactor free integers. Don't blame me. ChatGPT came up with it. Well, I coerced it into it. Okay, so the first one here is let's say all integers that start at 1. Yeah, so we're going to use this thing, and we have no cofactors at all. Yeah, I have been, hey, Otero, and I've been gone for a long, long time, that's true. So, let's say all the integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so on. Now the difference between these numbers is +1, right? So here you have +1, +1, +1, +1, +1, and so on. No. But I don't really like it that I put this in between. Now randomly we chose that 1 is not a prime, so let's start at 2. I'm just going to put it there. Now this 1 stands for that 2, right? So we know some starting point, and then these are offsets. Let me remove the pluses again. Which also doesn't serve much purpose. Oh, like that. So we start with 1, and then by adding 1 we get 2, and then by adding 1 again we get 3, and so on, right? So this is kind of like the sieve of Eratosthenes, or the sieve of Carlos. See description. We can remove here all the numbers that are divisible by 2. That's divisible by 2, and 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 that's 2, and 2, and 2, and 2, and so on. By the way, I can notate this series, of course, as a repeating series of 1. So I'm going to denote this by 1. And then the braces here just mean that it repeats. And we have to get rid of these, because this one is divisible by 2, and that one as well. Well, we do not really have to get rid of by this one, but you know, here prime bound cofactor free integers means that if I pick prime p to be 2, then we are left with all the integers that are not divisible by 2. That's basically what it says here. So that would be this list without all those even numbers. and so on. And as you can see, if we just take 1 again as the starting point, we have to add 2. So I'm putting the 2 here. 1 plus 2 is 3, and 3 plus 2 is 5. And then we add a 2 here, and a 2 here, and a 2 here, and so on. Now this 2 is of course those 2 combined, and this 2 is those 2 combined. But, well, since that repeats anyway, I can write this one also as 2 repeating. Then we do the next step of the sieve. We're going to strike out all the numbers that are divisible by 3. As well. So that's the bound thing. I mean, if I pick prime, so this thing is going to have a prime number, right? Maybe I should steal a little bit from my previous version, because it's not all that bad. Not 100% bad. Wait, part. I had a class here. With the comment. Well, actually, I want to copy this one. Did I do both? Sorry, hold it up. Yeah, I'm not sure about those actually. I'm just going to copy that. What the hell? Huh? This did not work. Thought I did the shift V, but apparently no, I didn't. Shift V. Yeah, here, now we have it. Y next P2. So we have primes, and my primes do not get very much bigger than 32 bits. And the index therefore fits into an int, I think. And then large integers, well, whatever. The distance between 2 primes, let's give those their own type as well. List of primes, put in a vector. Yeah, why not? You know, here we have all the primes that we generated so far. And then here, this is the class that I already started. So class representing a vector for integers. Factory. Factory for integers that are free of prime cofactors up till and including a given prime, right? So if my prime here is p, then p is equal to 5, then that means that the integers that this factory is generating are not divisible by 5, but also not divisible by 3, and also not divisible by 2. That's the explanation of it. So here we have all integers, and here we have all integers that are not divisible by 2, and now we get all integers that are not divisible by 2 and not divisible by 3, which means we have to strike out this one because it's divisible by 3, and that one, and that one. And then we are left with the first one, this one. It's now left, so we have 5. Oh, the 1 was here as well. I mean, the 1 is probably also not... Well, 1 is not divisible by anything, so that's good. Okay, so 5 is left, 7 is left. The 9 we just cut away because it's divisible by 3. And we get 11, 13. The one is removed again, and all the next one is then going to be 17, right? Let's add that here. 16 is gone. Okay, one more. 17. Well, maybe a few more. 20, 21, 22, 23. That is an offset of 1. And then the ones that we cut out here are the even numbers. So those are gone. And then here we have left 17 and 19 and 21 and 23. And then the difference from between those are repeated 2. Now here we can also cut out the 21. And then we are left over with 17 and 19, 23. And now we can see that the difference is, well, 1 plus 4. So I put a 4 below this one, it just means that 1 plus 4 is 5. 5 plus 2, 7. 7 plus 4 is 11. 11 plus 2 is 13. 17 plus 4. That one, 2, 4, and so on. And yeah, that repeats after just these two. So this here, well, I'll put it here. This here is my brown bound go-free factor integers where p equals let's say 1. I don't know. We don't have a prime there. And here at least we got rid of everything that's divisible by 2. So this one definitely is where p equals 2. And then this one is one that belongs to p underscore equals 3. Yeah, but that means that also the 2's are gone. Maybe one more, because it's still a little bit short. So now we're going to cut out the next prime, which is 5. Everything that's divisible by 5 is gone, so that one is gone. And the next one is not even in my list. The next one is going to be 25. Oh, that would be 24, I guess. 24 is up here. Okay, I'll even have to make it longer then. 24, 25. Right. And the numbers that are left are 7, because this 5 was gone. 11, 13, 17, 19, 23. And then the 25 is gone as well now. Yeah, it's getting too short. I don't want to put this all manually. The jump here is +6. Maybe still have it on my screen. No, this. By 2. So that's +4. plus 2 plus 4 plus 2 plus 4, just like before. But now this one's gone, so then the next one is plus 6, so that's 29. Oh, what the fuck, I just added here. 25 space, 26 space, 27 space, 28 space, 29. And then we get 31 for the 2. Oops. And then it repeats. But we need all of that. In fact, oops. Yeah, so the whole thing here is just what repeats. It repeats after the total sum is divisible by all the prime numbers. So let me add here the sum. Well, I put it here. So the sum is 1, right? It's just the 1 here. And this sum is 2. That's 1 times 2. And this is 2. Oops, sum is 2 times 3, 6. And this sum is so p underscore is 5, and the sum equals 2 times 3 times 5, so 30. Right. Okay, let's code something to generate these things. What are the crucial things here? Well, of course, I want to store this array here inside it. Looks like a vector. Let's have a peek again on what I did here. I call that gaps. I can just copy this one. Yeah, it's not really the, let's say, the gaps between the integers, because I'm going to generate everything now, I think, at once. So this is going to be this is gaps here, 1 and then 2 and then that and then and so on. So my default constructor is going to create the first one, which means that we have a problem because it isn't even a prime. This p is 1, so it doesn't have an index. You know, for the sake of beginning here, I could begin here, but well, I don't want to. I want to begin here. So we're going to call 1 a prime, which means that this is now index 0. And 0 refers to p is 1. Okay, so index 0, comma, p is 1. I want to get the whole thing at once, so we just have to fill that one in. So this one is 1 piece of 1. Then we have everything right. So let's do that. Make it. Let's call this Sieve. It's a little bit shorter. Now we're going to print the Sieve because we want to see what it is, right? Okay. Printing it, well, I always print using print on stream reference OS const, but print standard out stream reference operator less than standard out stream reference OS comma Sieve. We turn OS and then here we just call on Sieve print on OS. Boring but true. Let's implement that one down below here. It's not that interesting. Okay, I kind of want to see everything, I guess. So we have to I'm not sure about the spaces though, because it's going to be big very soon. Let's just print this and then generate some of the numbers. So we print to OS that, and then we run over all the gaps in gaps. It's called gaps. Yeah, gaps. Maybe put P in front of it as well. Or maybe index or P. So we do, I think P is more human readable in this case. So P is P, and then yeah, put a space after that, I guess. So we run over all the gaps, and then we add space G. Do you want to call like equal distance, maybe? No, just one space. Print all the gaps, and then we print and don't have a space here yet. Closing brace. I think I'm gonna go to a new line here. And then let's print for, yeah, let's just count. So we have a counter, 0. How many shall we print? 10. And then so we print some number n. Let's do this with or without commas. Just some spaces in between it. I mean, this is going to be this series here. I think I'll just put a space in the beginning. I'm lazy. The space separated. And we begin with these are integers, right? So in integer type n is 1. That would be the first one, and then we add the first gap. The gap index. So the gap index starts at 0. Let's see. So we start now. We're printing 1. It's this one here. And then we add the first gap, for example, this one here, we add 4, and we print 5, that's the next round. And now we add 2, so we print 7, and now we add 4 again, so we have to go to back to the start. So after here we have to do increment I, but if that then reaches the size of gaps, yeah, something like that, then we have to start over at the beginning. I think that should do it. Does it already compile? I think so. Oh no. Where does this even begin? Huh? What? See that again? That's a lot of errors. Okay, it's kind of explaining it, I guess. It doesn't even know what my types are. The standard ints would have those things. Would be nice to have a vector probably. Because of that. What else do we need? Already have IO stream. I think now I'm good. Nope. Not even close still. What? What's talking about this time? Request from a print on in Sieve which is of pointer type. Huh? Oh, I put a star there for some reason instead of a reference. Why did I do that? Plus a reference, of course, otherwise I wouldn't even call that function. Yeah, wait. No, that looks good. I don't know, man. Let's try it again. Non-member void something cannot have a CV. What do you mean non-void? Non-member. Oh, I didn't say what it is. What the class is. Finally. Right, so that worked. So P is 1, which is not a prime, I know, but okay. And that means the offset or the gaps are just 1 repeated. And then we get a sample starting at 1. Add 1, add 1, add 1, add 1, and so on. To create. Now with this one. Now we want to do the next one. This one. And I want to generate this one from the previous one. That probably needs a pointer to the previous one then. So let's say, yeah, maybe I should create a factor of those as well. Let me create a vector of those. So we have a standard vector of that. I just lazy call it sieves. All sieves created so far, generated so far. Generated sieve so far, where the index is the same as the index in prime. Right? To index 0 corresponds to p being 1, just like here. So this is now just the index. It's the prime index, so this one, but it's also the sieve index then. Use the same index as guy uses. Do I have an index for my? Yes, of course, prime index. This one. This is prime index type. Right. What to do? Well, that means that I should probably change this bit. Let's just say we construct the sieves here. Push back something. Push back nothing. Is that possible? No, it's not push back. And place back. Place back, passing nothing to the constructor. So that would be my sieve. So can be const, I suppose. Const reference sieve is now equal to sieves back by reference. I'm not happy though, because I was planning to. No, never mind. Well, I'm still not happy because every time I add something now, it's going to move stuff because this is a vector. It's going to move stuff in memory. No, that's not a problem. It's really going to move it. So that means that this vector, which is pointing to allocated memory, which might become very large, that's not going to be moved. It just changes the pointer. So that's okay. Let's see, still works. Oh, hopefully. So let's now create another one. So I'm gonna do a place back, and now I'm going to pass. Now then, not a pointer to the previous one because it's stored in a vector, and so it's gonna jump around the memory. But we can create it from the index, right? So we're just going to pass an index, and the index must be 1. Let's call this a bootstrap again. See that's a bootstrap. I want to print it. Let's say do just begin with that. Print it while index is less than 2. It's not a v2. Maybe it should be a for loop. I don't know. But the index was a prime index type. Should we begin at 0? No, I want to, this is 0. So yeah, we have to begin at 1 here. No, it's kind of silly. I want to start at 0. So I'm going to do ++ index in here. So we still do the same thing as we did, and now we push back to the sieve another one of these, passing 1. And now then is the index to the constructor, passing 1 to the constructor. So we need a new constructor, otherwise it's not going to compile. Constructor, new constructor here. And this constructor takes prime index. And let's not do that in line here, but somewhere else. Thinking about, no, let's just put it below the class for now. Constructor. So the index is clear, and that's just the index. And then, yeah, I need to prime. I want to have the prime number here. I don't know why, because I didn't use it yet. Just this. Well, we're probably going to need it. So let's store it. And I wouldn't know how else to do that than by saying, well, let's hope for the best and think we already have it in all the primes generated so far. But of course we don't. And then here we fill in gaps. Yeah? Gaps also has to be, let's say, the big challenge. But concentrating on this one first. The one that we create now, passing index 1, just reads prime index 1. It's crashing because it's an empty vector. So I have to put that prime into it as well. Now eventually I can use this to generate primes, but I don't know how yet. So the first one is 1, which is not a prime, but I'll just skip it then in the end. For now I'm just going to put 2 into there, right? So, okay. And we have also index 2. Oh, wait a minute. While index less than 2, but it's the next index, right? No, you're going to increment it. So this one is going to be 2. Going to pass 2. And then we stop. Maybe not the best thing to do here. Do while. It's not like while, maybe better. Try that one. While. No, also not. What the hell? I'm gonna leave it like this. Anyway, index 2 is also being used. So this is 0, 1, and then 2. I'll worry about the filling the primes in a natural way later on. These are the ones that are going to be used. Now we are not filling anything yet in gap, so gap is going to be empty. I wonder how that looks like. Oh, it's still crashing. Oh, right, yeah. So gaps is empty. We start blindly reading the first gap. So it just doesn't work. I have to put something in gaps. So let's cheat again and put 2 into here by default. It's an incredible cheat because that's already the next one that we need. This one. The default constructor puts 1 into it, and then the next constructor puts 2 into it. So that should work then, but this one is going wrong because we just put 2 in it. And it should have been 4 and 2. And I, for some reason, only print the first 2. So this is correct. So we begin with the 1 and then we print all the odd numbers. Yay. Thought I would get another one. This should crash. What am I not seeing? create the first one. Oh, I'm forgetting this one. This is index 0. And then, yeah, index is 1 is being pushed here. And then index is 2, so we do it one more time. I should get 3 outputs. Am I not crazy? I don't. I'm probably crazy. Let's compile this with debugging. I want to see what happens. So just to make sure, GB break main run next. That's the first one here. Yeah, so the default constructed one is that. And now we construct one with index 1, I think. Oh boy. God, I hate this. Oh, that's back. I hate this. Still back and place back. No, we are back. No, we're not really. Oh, it did in place it. Okay, well, whatever. So index is now 1. Yeah. Oh, well, it's, yeah, well, yeah, okay. So while lesson 2 is 1. So we only, why is this so confusing? I didn't print it yet. Oh, I'm getting it. Oh, yeah, okay, I'm getting it. So I'm constructing it here, but I'm not printing it. I'm an idiot. Yeah, we knew that, but I didn't know how. Now I understand how I'm being an idiot. So I construct the last one, but don't print it. So what's really missing is then, I guess, print at the end or something like that. Or maybe I should do... make this part of the bootstrap. Is there no way around it? That's really stupid. Or a break in between. If something break. Maybe that makes most sense. Forever. Print the current sieve, which is index 1. Sorry, 0. That's the first one. And I want to print 1, 0, 1, and 2. So at the moment that index is 1 still. Nah, just this is less confusing. So we increment index here, and we demand that that is equal 3. I don't want to print it. I don't want to generate it. If I generate it, I also print it. Yeah. So the prime number goes to 2, but the repeat is still just 2, so it's just still have the same output as here. There should have been 2, 4, another 4, 2 even, I think. Another question is, how can I create that from the previous one? Yeah, 4, 2. So I want this in my gaps. How can we do that? Well, now in reality, this is just 3 times the repeat of that one with a short circuit in it. To add that in as a comment. So what we really have here is 2, 2, 2. And now we realize that we have to combine these two, which then gives us a 4, of course. Add them up. And that leaves us with 4, 2. Yep, and then after that we get 5 times 4, 2, 1, 2, 3, 4, 5, and we have to combine apparently these two and these two, which then gives us 6, 4, 2, 4, 2, 4, 6, 2, which is what I want. That's this list here. Now creating this is rather easy. You just loop 5 times over the previous one. So in principle, we want the previous one to generate 2, 2, 2, 2, 2, 2, correct? So we just get all the gaps. And this one must generate 4, 2, 4, 2, 4, 2, 4, 2, and so on. And that just begins at the beginning. Pretty sure about that, yeah, 2. Let's add a few nice member functions, like, do I need a reset or something? Maybe I need a reset. I don't feel I need a reset, so I'll just make it empty. It doesn't do anything. How lame is that? Maybe I should make it do something. Anyway, after that I want to get a gap. We call that next. And that should give me the next gap and the next gap and the next gap and going around. And that means that we need internal state like an iterator, but I'll just put it inside this thing. And I could use an iterator, but why not use an index? I think reading the size of a vector is like fast. I mean, the vector just stores its size. So might as well use an index, I think. The number of gaps, gap index, current gap index. So the gap index starts at 0, it's the first gap. Or we don't initialize it at all and then fill it in here, why not? And then next would you Now let's put it on multiple lines. We have to increment the gap index, that's for sure. And then I don't like it when it is equal to size. I always set it to 0 again, so that rotates. And I have to return the current one. So I think I have to do something like gaps, gap index, and return gap. I think that should work. So that goes around and around. Okay, so now we need the previous one, and that should already be filled, so it can be const. Previous one is Sieve's our index, and I don't know which one to use, you know, this one or that one. Our index, I don't know which I'll pick one. Okay, I'll pick that one because it's shorter. -1. Because you store all sieves in the sieves vector. And the previous one is just, well, the previous one by index. And then we can call reset on the previous one. And then we can keep calling next on it. Hey, hi Zas. And everyone else. What to do here? I think we need to know when to stop as well. So I think I need to keep track of the sum. Think very big. Integer type is my big type. Call it sum. Well, we have one sum of value 1, so the sum of that 1 is 1. And the next sum is equal to 2 because it's the previous sum times p. I don't have to calculate, can do that here right away, I think. Gaps, we don't have gaps. We're gonna have to do gaps later on, but some I already know. Actually, that would be involving this one. Yeah. Okay, I'll do that here then. Previous sum times p. So the sum of all gaps is every time the sum of the previous one, because that's how often we're going to repeat it. times a new prime, which means I need an accessor called sum. Put them in reverse order, I guess. What's my sum? Integer type. Sum const return sum. So now I know the sum, the total sum of all the gaps. When you're going to fill gaps with the new gap. And then we have a sum, which we add gap to. And then we continue while that sum is still less than the sum that we want or need or whatever. And the gap is prime gap type gap. I'm just going to get gap from the previous one as well. So we did reset. And I can do next. So this gives me, let's say the previous one was 2 repeated, then this gives me 2, 2, 2, 2, 2. And then we add that until we get 6, and then we stop. Which is all nice and dandy, except that we don't want to have 2, 2, 2 in it. We want to have 4, 2, 2 in it. But for now, I'm going to see that this works. And of course it doesn't compile because Sieve was not declared in this scope. Really? Pretty sure I called it Sieves. I didn't. That's defined below the class, I guess. Here it is. What is this? Passing const as this? Yes, not const. Previous const. You cannot reset previous. True. It's not const because you have to reset it. Some invalid use of member function. Seriously, didn't define the sum here. It's just an integer, I think. Integer type sum. Yeah, we got stuck with the ones, but still. So this one is a 1, and now we have 2 of them, and then we have 6 of them. That's going in the right direction. Now, why is this 1 here, 1, 1, instead of 2? Well, the reason is that we didn't realize that 1, well, actually this one here, 1 plus 1 is divisible by 2. So that's why we should have skipped it. I want to find a faster way to do that, but for now I'm going to be lazy. Let's see, where are we doing this? Here. But the sum plus the gap. Why am I not working with that plus 1? Because that would be the integer. Let's call this n. Now we started 1. Now we add a gap. So now it's just the number n. Yeah, so this gap represents that n. And we want to continue until the sum is less than some underscore. So that becomes less than or equal, if I'm not mistaken. N. Because n is 1 larger than the sum. So now if it is equal, the sum itself is still less than. Yes. And then we just want to skip if n percentage p equals 0. Gonna try this. Oh, that did not work. It skipped it. It skipped it in a way, but it just vanished. It just evaporated. There is no. It stored 1. I should add it to that. Yeah, that was silly. So what's happening now? I had a 1. Oh, wait, what the hell, man? I have to remember that gap. Yeah, I have to think. So we get here, let's say we get the 2. This is 2. We add 2. 2 is divisible by 2. What I should do is get the next 2 and add that to this 1. Let's do an equal. We want to do something like get the next one, and I think that I don't have to test that again, because it's impossible that it would be again the case. So now I can just use this gap. like that. Yeah, this n follows the gap summation, but if it's divisible by p, then you skip it by doing the same as we did here, but adding it to the gap, adding that gap as well. Sorry, that's not correct. Now I'm adding the first gap twice, so that's not good. Should add the previous next here. What is next returning? Prime gap, of course. That worked. In fact, I think it's kind of finished, except that I want to make it faster. So we should be able to do, let's say, one more. No, two more, one more, two more, two more. Oh wait, no. We still have to fill the primes here. How do we do that? So, let me see. Kind of sneak these push backs in. Which one did I really need? Like for the first creation already? It's like this one? No. I need one. I just need one extra prime for each time I call this one. So the moment we call this for the first time, and that would be with index is equal to 1, it's going to read 1. Yeah. So I do need these two. I need this one for the first time we get here. And if I'm going to push 1 prime per loop here, then I need just this one for the bootstrap. And then I need to be able to push a prime before doing this. After doing that. Is that possible? I have no clue because I'm stupid. Let's deal with this. So the idea is that before we can do that, we have to push a prime. The next prime, and I want to get that prime from the sieve. Isn't that like 1 plus the first gap? Sieve dot first gap plus 1, I think is should be that prime. Const discard something. Oh, first gap. Guess that worked. So now I have, this is all the integers. These are all the integers that are not divisible by 2. And these are all the integers that are not divisible by 2 and not divisible by 3. And these are all the integers that are not divisible by 2 and not divisible by 3 and not divisible by 5. But more importantly, we have these. And this one and so on. Maker asks why you didn't put the if ++ index equals 5 condition in the for statement, because there's a statement afterwards. This is in the middle. We do statements before it and after it. So we cannot put it there. I mean, normally this is part of the loop condition, either the middle thing here for the for loop or some while. But if I do that, then I have code duplication, and I need to duplicate this or that. And if I do it like that, then I don't have to duplicate these code blocks here before and after. That's why I put it in the middle. Okay, so I'm going to make this even bigger. Right, okay, there's a few things that you can say now. There are two things that need to be done here to optimize this further. We can stop at some point because this blows up very quickly, as you can see. That array gets humongous. Like this is going to be slower than the Sieve of Eratosthenes. And I just wanted to make it faster by not having to do the modulus. I don't like the modulus. It's the whole point, of course, of the Sieve thing, that you don't need a modulus. That modulus. So not a faster way we can predict this. For start, I would like to get a feel for this by printing the number of times we have to do this short circuit, because to be honest, I have no clue. So every time this happens, I'm going to increment a counter. It's called short circuit. Add it to the class. Where's my class here? And then print it. Print it at the beginning. Short circuit equals short circuit. As if we need this. Boing. Circuit is 0, 1, 1, 2, 8. It's a weird value. 48. Whoa. Okay, well this is blowing up so fast that we don't want to print it anymore. And then we can print a little shitload more, I guess. Well, actually, maybe not print this, but we do want to print the sum of everything, but it's just, yeah. Multiple every time. It's sort of a factorial, but then just the primes. So it's like 1 times 2 times 3 times 5 times 7 times 11, and that's an interesting new function. The Carter-Wood factorial. And the number of elements would be interesting though. It's just the size. Okay, let's print that. Just the size of the array. So instead of printing... Okay, let's not print the elements here. Instead, we print the sum, which is surprisingly sum, and the number of elements. Caps underscore size. On this also very rapidly makes no sense, so let's just not do this at all. So we can stop here. It does not feel right. Does it feel right? Oh, wait a minute. It does feel right. Ooh, how incredibly interesting. Incredibly interesting. Incredibly interesting. I guess it's logical that the short circuit of this one is equal to the number of elements there. I guess that is logical. Yeah. Well, that means that the number of elements is very, very predictable as well. Wow. Yeah, this is super interesting. Let me print more though. Where's that new line coming from? I want to get rid of that one. Here. Don't need that anymore. Kind of scared to do 20, but oh, and suddenly it's not fast anymore. What's my memory doing? My memory is running up. I mean, it's really growing out of bounds, right? This is the number of elements, so yeah. Probably have to stop it before I run out of memory. Hope the video still worked. Let's think about this. Let's say I want to generate all prime numbers till 1 trillion. So 1 with 12 zeros. Then I think I only need really prime factorization till 1 million. If that is the case, then we could already stop about here. So it would be pretty doable. Well, we still need a rest, but I don't know. At least it doesn't make any sense to make it grow that big. This is like literally the offset. To add 1 to this, and that's the number we're talking about. So that would be, this is already like 6,000 times too large than what we would need. So you only need to go to 1 million. Whoa, this is already 9 million. Don't even need to complete this one, and that was already pretty fast. Right. But let's keep it simple. I'm going to try to generate all primes till 10,000, say, for which I would only need to know all the primes till 100. Yeah, because if a composite number between 100 and 10,000 is composite, it will have a factor of something below 100. Something is not right, but what is it? See, the point is that this one is already capable of generating all primes all the way up till 25. Well, which is wrong then. Because 5 squared is 25, and everything in front of it is indeed prime numbers, are prime numbers. So we get 2, 3, 5, 7, 11, 13, 17, 19, and 23 by just his first block. However, yeah, in order to do that, I need the full thing here, just both the 4 and the 2. And then for this one, I would be able to go to 7 squared. I have to go, maybe I should just do print this thing all the way up till that square. So that means I need to know the next prime at this point already, which is the case, I think. Well, not all the way in the beginning, unfortunately. I'll have to cheat, I guess. Yeah, of course you do. This is bloody 7 here. So this one squared is up till where this works. So this one can be generates all primes all the way up till 121. Or not, yeah, that should be the case. I'm going to print those, I think. So we resurrect that, and then we say print, well, print n is 1. I get the first gap. So I'm going to say integer type and is gaps underscore 0, right? Plus 1 times itself. And then I'm going to print all the way up till and including that. So we just do while I think n is less than or equal and see how that works out. Now I need a quick way to test if this is correct. Looks correct, but yeah. Are these really all primes, except the last number? Sure they are. Hey. Yeah, we're running out of memory again. So let's stop this. Yeah, now what? So I guess my point is that no, there's no point yet. I just want to make it faster. So I know in advance, for example, we found this already. I just know in a nanosecond that we have 480 elements. So I know in advance that while generating that one, we're going to have 480 short circuits. There should be a faster way to find those than to do a modulo 5,760 times, or even more. That plus that times almost 6,000 times. Yeah, well, of course. Of course. Let's do, instead of the modulo, we're just going to calculate that number. I think it's a multiplication. Still not super happy with it, but I'm having the feeling that, well, the fastest way would be just if I knew in advance how many gaps I can add until it goes wrong. That you can just make a loop that copies stuff over, literally copy stuff over. Just call next, which is just reading from an array. To read from an array, and we return that. Okay, there is an equals in it, but it's hardly ever firing. So you can do this is very unlikely. You don't have a cache miss usually there. So that's really fast. Just I think memory bandwidth still. So we know in advance that, say, the next 1,000 gaps are just not hitting this, then we can do in a very fast loop. Read from array and add it and push it back. It's just copy one array to another almost. And then by the time that we copied exactly that amount that we determined in advance, then we know that this is going to happen. And we just add the next one to the previous one a single time and then do that again. That's like super fast. But the question is, can we predict that? Can we predict how often we have to do this until that hits? So I need a new counter, I think. I need a counter that says what these numbers are, and then maybe you can figure out if you can predict them or not. Let's print out that we enter here new constructor. And then reprint. I'm just going to have a count 0 times, and now after adding that once, we did it once. So let's increment that, and then when we run into it, I'm going to set the count to 0 again, of course, or print it out. Count. I don't know. It's probably going to flood my screen off. So useless. I have to stop sooner. Way sooner. Where's my main here? Yeah. Index is 8. It's still a lot, actually. Too much. Okay, well, let's write it to a file and then look at the top of the file. So this one is just printed 1, and now we get 1 6. And then we get this. Interesting. Is that a palindrome? 25. If you strip off the 1. Why is there a 1 at the beginning every time? Every time. But yeah, 33, 33, 8, 8. So it's like binomial. How's that Pascal's triangle thing? It looks like it. So it's, I mean, it makes me feel like I should be able to generate it from the previous line, although it grows a bit fast. Maybe I should just put it in the integer sequence database and see what it tells me. Or can we deduce this ourselves? How can you go from 6 to 11, 6, 3, 6, 3, 6, 11? Of course. No, yes. No, no, not really. Look pretty random, actually, doesn't it? Pretty damn random. But hey, you never know if you don't try. I'm gonna just start here. Let's forget the 1. Take a few. See if we find something in the integer database, which is the online integer database. Well, sequence there. OEIS. search. Oh, motherfucker, it finds it. Oh, yeah. Except that it doesn't help anything, because it's a prime gap pattern of compacting Eratosthenes Sieve. I think I'm not going to get rid of my childhood frustration. Because clearly this has already been done before by someone else. Compacting Eratosthenes Sieve. Yeah, that's what I'm trying to do. Story of my life. It's always done before. But do they have a formula for it? I'll blow it up a bit. Too small, right? Yeah, that's what I'm doing. Oh, it's just done before already. Right, no formula. Oh, there's a formula here. AN plus 8 is AN. This thing just repeats. That's not what you are interested in. Mm. $23 starts with 90. I don't think so. What is that for nonsense? Oh, it doesn't grow that fast actually. 25, 33, 54, doesn't grow that fast. So it said that the first number was another sequence, which was, where did I see that? Where did I see that? The first digit up here corresponds to. Yeah, so it is 90. So I have 25, 33, 54. Before that 11 is actually, yep. Not much information here, I must say. Just referring back to the primes. I'm just keep staring at this comment here. I conjecture that 25 and 64 are the only terms that are also square numbers. Next line. The next squares are which occur at position. What? Is that the disproof of the conjecture? Well, I don't know. Anyway, let me stare at it a bit longer until I have a feeling that there is indeed nothing to learn from this. I already read this. Equivalent sequences. Yeah, that's just the other ones. Nope. Nothing new there. Okay, so if I see a pattern in this, I did something new. But I have to admit it looks random like hell, except that it is mirrored. That's interesting. That is bloody interesting that it is mirrored itself. That is bloody interesting. I mean, that means that I only have to go through the half of it, which would be somewhere, is that true? 15.4, 15.9. Oh, it's not so, well, wait a minute. No. This 9 is that 9. 10, so now we're at that. 30, yeah, this is the middle. So I only have to do this slowly, and then we have the numbers. The rest of the numbers is what we figured out before. So those 4, 10, 19, etc. We already saw them. That's a speed up a factor of 2, maybe. must be a faster way to find this. Come on, can't be that hard. Let's reason about this. Let's reason about it. So I think there must be a structure. I'm not going to look at that because they are too large. What is a good point to start here? Eight elements. No, maybe I should print the elements, although this is already 48. See, these are the integers that are not divisible by primes below 11. And they are generated by this. You can delete that as well then. And that's the bootstrap. But yeah, let's begin with printing the elements after all. Again, the gaps, that would be this one. I don't know which one. Still one more. No, let's do two more. It's already ridiculous much, but well. Right, so these are all the integers, 1, 2, 3, 4, and so on. We stop printing at 4 because I know in advance that that's the first non-prime. Why do I know that? Because that's the square of 2. Well, where do I get my 2 from? Well, the 2 is 1 plus this value here. And that's correct if you ignore the 1. 2 and 3 are primes, 4 is not. And how was this generated? This was generated by adding 1 to 1. And that is this one. And then that's the only element. Elements, number of elements, only 1. sum of that one element is 1, but it's a bit too trivial. So we repeat that in a loop, so we add 1, and we start with 1. 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, and 4 is the first non-prime. Now the same thing holds here. We have only one element, which is 2, so the sum is 2, obviously. And we begin with 1 again, just like here, and we add 2 every time. And then the first non-prime is going to be the square of 3, where 3 is 1 plus this 2 here, which is the next prime number. So this prime number is that 2. Now this 3 here, which is prime number, is that 3. And then this 5 is that 5. And then every time that's the next prime number, so that's not true. I've added 1 here, but here I'm adding 2. So it's this value. So 1 plus 2 is 3, and there's this 2 plus 3 is 5. No, again, not happy. Yeah, well, it's 2, no. How do I get my 5 here? Well, 2 plus 3, but how to get my 7 here? What's this one? Oh, yeah, of course. So we go all the way up till the square of that value. And that value is the next prime. And that is 3 plus... No, it's 1 plus 4. Yeah, it's this 1 plus that 4. That's a 5. Sorry, not this one. This is no. It's just 1 plus this thing here. So in this case, it's 1 plus 6 is 7 squared is 49. And then everything before that is our prime numbers. All the prime numbers, actually. And so on. And now we want to know, we want to find this sequence here. Let's concentrate on this one. The fact that it always starts with 1 means that we always have to add the first 2 gaps together. So in this case we have a gap 4 and 2. And the first 2 of that sequence, it repeats, so it's 4, 2, 4, 2, 4, 2, and so on. The first 2 are always combined into that 6. And then for the next one also, 6 plus 4 is 10, 10 plus 2 is 12, and so on. But the reason for that is indeed quite obvious, because that's just the skip to the next prime number. So if you add 1 to this first number, you get the next prime number. 13, 11, 7, 5, etc. Which is exactly defined by the next number, usually or always. Yeah, it must be always, I think. Right. Then let's say okay, so I think that 1 is indeed always there. Now, where does this 6 come from? This 6 comes from the fact that this 6 is here and not somewhere else. More in particularly 1, 2, 3, 4, 5, 6. So we found this 6, and then we just follow this one here repeatedly, 4, 2, 4, 2, 4, and then the next 2 is not a 2, it's a 6. Combine that 2 with the next 4, and that distance is 6. That's this 6 here. So I want to see if that is correct. If you look at the next one, for example, here this 11 here corresponds to the short circuit of this 10. And then we repeat that one, but the 6 was already done. Oh no, where does this 242 come from? Oh my god. Oh, that's just this, sorry. The 10 is this. And then we get 2, 4, 2, 4, 6, 2, 2, 4, 2, 4, 6, 2. And then it repeats, so begin at the beginning again. 6, 4, 2, 4, and that's the first short circuit. And that distance is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, that's at 11. Sorry, this one is this 10. 11 is the 6 that we find after that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, that's the first. And then I guess this 6 is then again 1, 2, 3, 4, 5, 6. So that would be short circuit. And then 1, 2, 3 further. That 8 is certainly a circuit. Let me find the 6 as well. So you need to keep track of where we were in this range here. That 11 was, I have no clue. Do it again. 2, just 2. 2, 2, 4, 2, 4, 6, 2, 6, 4, 2, 6. Combine those two? No. Those two. And then we get 6, 2, 6, 4, 2, and then that 6 is those two combined. Great. So now we know how to interpret this. It's just to skip, well, that's how I calculated it, determined it in the program. But it's to skip in this series until the next short circuit. I'd say I don't find it logical at all that it is a palindrome. Not one bit. Why the hell is that the case? Okay. Right. I think I have to go all the way till here. This is way too short. So this is the first one that makes sense to look at. And then we know that the 11, etc. comes from the distance between these elements that are short-circuited. And these elements come from the repeat of this. And we repeat that yeah, from 30 to there, so 7 times. So let me do that. To repeat this 7 times. 1, 2, 3, 4, 5, 6, 7. And then the numbers those represent are, I think, 7 for this one. And this one is an 11. Yeah. Yep. So this one is 1 plus 6 is 7. 7 plus 4 is 11. Eleven plus 2 is 13. 13 plus 4, 6, 17. And well, basically these are just all the primes that we generate. Yeah, from here. So this is these numbers, but we stop at 49 here, but well, the thing continues. $49 plus 4, 53. 59, 61, 67, 71, plus 2, 73, 77, 79, plus 4 is 83. I'm going to go ahead and just change all these spaces here into 2 spaces. Although very quickly we need 3 spaces. Well, get it. How much is 83 plus 6? That is 89. Plus 2, 91. Plus 6 is 97. Plus 4 is 101. Okay, now I need to change all them into 2 spaces. Does that work? Probably not. Nope, does everything. Damn it. Substitute space with 3 spaces. Okay, plus 2, 103, 107, 109, 113, 119, 121. Plus 6, 127, plus 4, 131, 133. If I make a mistake somewhere, I'm just so fucked. Then everything after that is also wrong. 137 plus 2, 139 plus 4 plus 6 plus 2 plus 6 plus 4 6 1. Okay, I'm gonna cut them in 2 rows, I guess. One 6 3 1 6 7 1 6 9 1 7 2 1 7 8 180. I made a mistake because no way in hell that these things are suddenly even numbers. Yeah, that looks like the point. 171 plus 4 175 plus 6 181 plus 2 183 plus 6 189 plus 4 193 plus 4. No, I'm doing it wrong again. Plus 6 plus 4 plus 2 plus 4 plus 2 plus 4. This must be a 3. Plus 6, it's 9. Plus 2 plus 6 plus 4 plus 2. Mysterious. Plus 4 197 plus 2 and 9 plus 4 is 203 plus 6 is 209 plus 2 is 211. Yeah. Yeah. Was it worth it? So, yeah, now my short circuits happen when the numbers are divisible by 5, right? No, 7. So this one is also always cut out. So we get also always a plus here. This is cut out, so the gap becomes 10. Because this one is cut out, maybe I should put the plus here, so we know that the 7 is cut out. Aha. And then the next one that is divisible is of course 49. So that one is cut out. And then the next one that is divisible by 7. Now I don't want to say much, but if it's divisible by 7, we might as well divide it by 7. Divide that one by 7 is 1, and then we divide this one by 7 is 7. And then if we divide the next one by 7, I think we get this number here, right? 11. So that would be this one. And then we get 13 times 7. 13 times 7, 91. 13, 17 times 7, 119. That is 17 times 7. 19 times 7, 133. 23 23 times 7, 161. And then we get 29 times 7, 203. 59. Now in this case, and that's a sad thing, I guess, we do not get to the 49. I'm not convinced that it will never happen, because now we just have prime numbers or only, all of these numbers are just 7 times a prime number. And not like they don't have 3 factors. I think like in this case it really goes wrong. You get how much is that? Oh well, anyway, yeah. But it should work. If we just keep on going here, then this is the list. This is the list. It tells us this list times 7 is just the numbers that we will have to skip, I think. 2 plus 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 here. The rest is no short circuit. So the number of short circuits that I see is 1, 2, 3, 4, 5, 6, 7. I was thinking like it had to be 8, and I was just missing one. Here's another one. 8. Which is equal to that number of elements that we have in here. Obviously, because we just defined it like that. Or didn't we? No, we didn't. But it is equal to that number. Not convinced anymore. It's like these are 8 as well. I think these are the real numbers. So 1 and then 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No. Combine that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And combined with that, 1, 2, 3, 4, 5, 6. Combined with that, 1, 2, 3. Combined with that, 1, 2, 3, 4, 5. Combined with that, 1, 2, 3, 4, 5, 6. Again, oh, that's this 6. And now we have a palindrome. We go back with 3 again. Seriously, why? 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What is the reason? Let's test this first. Test this first. So instead of doing, and so what I'm doing now is I'm just adding gaps and then calculating the next number. So you have 13, add 4, get 17, add 2, get 19, and so on. And every time I'm doing a modulo 7. So on this number, and 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 modulo 7 is 0. But I think it would be easier if I just calculated 49 and then compared this 49. 49, yep. And so on. So that's faster, right? So that's what I'm going to do. And do we not do the modulo, but we predict what this number is, and that number is 7 times that number, which can be generated by the previous prime bound cofactor free integers class. The previous, right? Of course, because I'm generating this one, or not. I hope it's the previous one. In fact, it's not the previous one. We're doing modulo 7. So confusing. It's the one that generates these numbers. I have no idea what I'm doing here. 11. 1160. This one. Yeah. No. Yes. I don't know. Something. I'll think about it when I see the code. So now we're doing and percentage P. Let's say the P is 7 here. Yeah, it's the previous one then. It's the previous one. It's interesting because I'm also already calling previous next anyway. Isn't that highly confusing? What the hell? Okay, I want to change this condition into if n equals next failure. So we need an integer here. Next failure. And the first expected failure is the very first number, right? Because it's always failing the very first time. At count equals 1. That's why it fails. So the very first thing already fails. So 1, that's this 1 here, plus the next gap. So the next failure is like literally whatever next returns now, which is just the first gap, plus 1. So we can do previous first gap plus 1 is the first expected failure. For example, in this case, don't mind me being confused. Just in this constructor, right? P is 7, so the previous thing is this one. And the first gap is 6, plus 1 is 7. So 7 is the first failure. And it is the first failure. Yay. And then we have this. Circuit, get the next one, add it, and so on and so on. But now we have to calculate the next expected failure. So here we calculate, or maybe not here, put it there. Next failure equals 7 times some other number than 1. What is the gap that I just read here? This gap is 6, right? That was the whole point. Now I want to use the next call to next, but that's this G here. So in the case of P equals 7, the previous has the P of 5. See, my brain is getting too old for this. I just can't get it all in my head at once. Getting confused. First value was 7, now I need to get 7, so that I can multiply it with that 7 and then get 49. That 7 is of course equal to this 7. And then after that I need to get 11. Probably should just store all of them. Because, or maybe I should, I don't know, maybe it's easier to not store them. I don't know. It's pretty annoying though. Reading this one, I definitely need to store all those values then. I don't need to store a billion of them though. The last one is 29. I just need to store these values. I need to store that many. Is that true? That includes because the last one that I need to store is 29. 1, 2, 3, 4. 1, 2, 3, 4, including the 1, I need to store that. I don't need to store the 1, do I? Well, maybe. I could read them in advance, maybe. Could read them in advance and then use that. Use those values for the thing that I have now. And then when we run out of that, I go back to reading the remaining values. At which point, I have to say, yeah, I think I'm gonna do that. So I need to know this 8. How do we find that out? That is the number of elements of the gaps, so the number of gaps of the previous one. So we need a function. It's going to be slow because I have to switch back and forward or I just lose it. Well, I can literally switch back and forward by editing them both. I need a function that returns a number of gaps. Step 1. Number of gaps, well, it would be a size type, but I hate size type, so let's make it an int. Is that allowable? Gaps. Const. Return gaps size underscore. So a function that returns the number of gaps, and then we go back here. And I'm going to do something in advance, meaning like whatever here. Previous gaps. That gives me 8. So let's make a vector. A vector of something with the size of gaps. Does that make sense? And what I'm going to store in it, I'm going to store in it the first prime numbers. So basically this, right? But those return gaps. No, I want to store n in it, so I'm going to store integers in it. Integers, yeah, just the first n integers. Let's call that cofactor free integers. Ends. I know, man. The first gaps ends, and then we have to fill that. There's nothing special about it. I just want this value for the first n. So maybe you should make a loop. I pass the size in advance, so well, not the size actually, so that's nonsense. Okay, I set the capacity. Capacity is known in advance. Don't call milk for nothing. So I really need to store that sort of thing though. So God knows what variable name I have to use for that one. K. Caps. Capacity K. K. I think I need to, as a comment, I'm going to add this case here. What we're doing here. So we're reading, let's say, we're gonna assume that P is 7. So let's assume P is 7 here. Well, then previous P is 5. Yeah. I guess so is equals whatever. The number so that's this thing. which has stored 8 gaps. Yep. Read eight values from previous in advance. So the first time we call next here, we get the first value. Actually, I don't even know. We have called reset, and then I think next returns whatever reset set itself to. Yeah. That is the first gap. I just get next is returns gaps. Hello. So it's actually gaps. Read those gap values. Use in advance and convert them to corresponding integers. Yeah, that's what I want to do. So this is not what I want to do. I want to have an integer n. I'm gonna reuse that here. Also have to set to 1. Just going to do what we do here actually. Just add it. So I'm going to read a gap here. And calculate the corresponding n. And then push that n back. So that means that we are reading here 1 plus the first gap, which is 6. So that it would be 7. And then we add 4 to that, so that's 11. And then plus 2 is 13, 17, 19. Plus 4 is 23. Plus 6, 29. Plus 2 is 31. But the last one we don't need, actually. Like literally, we don't need it. I'm going to do less. Read all gap values except the last. From previous in advance and convert into corresponding integers. So then we get those values. So we go gaps minus 1. So the capacity now is 7. 7. We are going to store 7 numbers. And we call next 7 times and we store that. So we just don't store the 1, then you have these values. And that's what NS becomes. I'll add it here. NS is that. And then we can do a failure index. Int failure index is 0. We can use that in NS, so get 7 and multiplied by 7, and we get Oh, well, I might as well start with 1 now I think about it. Can we do that? Yeah. So failure index 0 refers to that 1. But I don't really want to start with that. Wait a minute. Yeah, well, let me see. I want to do. It's a bit silly to do it this way though, because I just know that value index is 0 and therefore that NS0 is 1 because I pushed it back here. So this is just multiplying by 1. So I'll remove this part in a minute, I guess. So I begin here with next failure is 7. And now I want to read the first previous, but we already did that. We did that here. So I can't do it again. We have to make a second loop, I guess, that prevails for the first calls, first k calls. We called next exactly k times. I'm going to make k const, so make sure that it's not changing. To make clear that it's still that thing there. So k here equals 7. Okay, 7. Call previous next k times. I don't think I'm ever going to reach. Okay, I'll just kill this off right now or not. And I just have to think of it again. The next failure is always P. Now we're going to redo this loop. But I don't need to do a while loop because I just know that the while never fails. This statement never fails because we'll never reach the end. We just have to do this exactly k times again. This loop lasts k times. But then we're going to do exactly this thing here. Except we don't call previous next. Instead we're going to use ns I. But then I must be start at 1. So the first next gives us a 7. We had pushed back a 1 in front of it. So in order to get the first next, that would be index 1. So we start with index 1 and then this becomes the first one. And then we do n with n plus gap. Let's just repeat everything here. And this next failure even. And that's always the case actually. So well, the first time around anyway. I just set it equal to p. Which is like, yeah, well, okay. Always fails, but doesn't matter. Maybe we can speed that up as well. But it's hardly a super speed up. And then we do that, and then we do that. But we read the next I again. So what I want to do here is maybe do a plus plus I actually. And then not do the plus plus there. And then start at 0. And I'll make this a less than. And then I can just do plus plus I here as well. So now we start reading with the index 1 and we just read the next one every time. And we continue with this gap and print count to 0. Next failure. And then there's even more. This last line as well, I guess. So full duplication of this part, but instead of calling previous next, we get stuff from the pre-read NS array. And I still have to fill in the next value. But we have that covered now. So the next value is P times the next failure index, so times NS, the next failure index. So it was 0 incremented to 1, we get 7. So now we get 7 times 7, next failure is 49. Yeah, and then the next failure is 77 and so on. So we detect them. But we stop after k times. Why? Because if I is equal to k, then we would be reading index k plus 1, which doesn't exist. But k itself should still exist. So k is 7, index 7 should exist. Well, it does. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, so that works. And then after that, we can continue here because now previous next is just going to pick up where we left. And the next failure then here is, well, just still the same things here. Vector has no capacity. Set capacity? Dude. Oh. Is this possible? I don't know that. Vector. Cap. capacity reserve. Yeah, hello. Reserve sets the capacity. Could have known that. Out. I don't think it worked. Nope, totally not. Actually, these look still okay. This looks wrong. Four two is okay. This is wrong. Excuse me. Well, I'm happy that the bootstrap works. Okay, so what goes wrong? This one goes wrong. This is what we should have gotten. Well, it looks like the 4-2 is being repeated. Sum is 30. Well, it's not really 30, is it? This is 6 plus 6 is 12, plus 12 is 24, plus 7 is 31. So if that is a 4, I just have it 1, 2, 3, 4, 5 times repeated. Yeah, that's what we expected. So if this was a 4, then it's just 5 times the 4-2 repeated without any short circuit. And this looks like totally different. Don't want to even look at that. Need a breakpoint at p equals 5, I guess. Well, better at this point here, right? So whatever the index is, at the moment you calculate something that goes wrong. But what? It'd be nice if we had some output here. Oh, we have output here. This output here, that is, yeah. There is no output at all here. Okay. So index 3 is definitely not good. Now I've got again what function that is. It's line 89-ish, line 90. TB. Break main. Let's do break 90. I don't know. Condition 2. Index equals 3. Continue. Previous. Print previous. So previous is prime 3, which is index 2, and for to repeated sum 2. I think it's okay. Then the next sum must be 6 times 5, 6 times 3. Well, index is 2, so now we're going to calculate 5. So print p underscore is 5. Yeah, so that's 5 times 6 then. So it's 30. Previously set, so that just sets gap index to 0, there's nothing. Oh. Okay. Previous is 2 gaps. So we are going to read only one of them, that's the first one, 4. And k then being equal 1, we're going to make an ns that is equals 1 and 5. So nothing else necessary is the question. We'll find out in a moment, I guess. Oh, that's not correct. Sorry, it doesn't actually. That's not a bug, but it's annoying. And I can look at troop again because we're actually not dealing with the one that I have my comments for, but the one before that. That totally goes wrong. So this is previous, and now we're going to try to generate that one. So let's do that as well then, I guess. So I have 4, 3 repeated. 2 repeated 5 times. 2, 3, 4, 5, which corresponds to 5. So 1 plus 4, 5 plus 2, 7, plus 4 is 11, plus 2 is 13, plus 4 is 17, plus 2 is 19, plus 4 is 23, plus 2 is 25, plus 4 is 29, plus 2 is 31. Short circuit, the first one should always be a short circuit because we're going to remove all multiples of 5. And then the only other one that's divisible by 5 is this one. 25. Which means 1 and 5. So yes, that's the only numbers that we want to read. Which are these two. So NS should be 1, 5. And then we're going to filter 5 and 25. Let's copy this inside. Okay, reserve 2, so case 1. Push back 1 and then push back 5, right? What I said. That should be correct. This is 1 plus 4. We have n is 1. The gap now that we read is 4. So now n is 5 and we push back that as well. And then we're done already. And ns is now 1, 5. God, totally correct. Didn't change anything except for the reserve here. So we continue. Set n equal to 1. Next value is p. P underscore is 5. Okay. So that's actually this p times that 1, but I removed that multiplication because it's always 1 anyway. And then we read the first gap, which was 5, right? So next. Gap is still 5, n is 1 again, so we're going to calculate. Wait, that's not correct. I'm reading it from ns, but I didn't fill. That's the reason. I didn't put the gaps in here. I've put the n in it. So is that then the case that I just can say n becomes that? Just addition is not n. This n is just equal to that ns. Or do I need a gap as well? I'm pushing back the gap here. I need a gap because I want to copy it. That's it. That's the reason. Yeah, still need to keep it. Ah, fuck it. Okay, stupid. Okay, let's just read previous gaps then. So instead of everything changes. Prime index type, previous gaps. No, I'm not happy. Let me think. Yeah. Need all gap values except the last from previous in advance. Do not convert. Adding a leading 1 to actually use gaps becomes that. No n. Previous gaps reserve k. Don't do that. Gap n plus n. Do I need that? Not really. Previous gaps. Push back gap. Well, there wasn't any need for that then. Let's see if this works out. So should be that, then previous 5, which is for 8 gaps, read all gaps, We just read all gaps except the last one. Joe, hello. No. Very, whatever. Yeah, that's just silly. I'm not doing that. Well. Okay, so this is then previous gaps. Gaps is just a number of gaps here, right? Doesn't read really well. Yeah, let's call that the number of gaps. Well, that totally does it, I think. But now I don't have an NS anymore. And NS is being used in this first block, not afterwards, obviously. Oh. It is. Okay. Well, no index failure. We're just going to do... Well, I do need an index failure. But I need an NS as well. So does expected failure then? Again. So my first expected failure is... well, that is next failure actually. So next failure. Okay, so what the hell, man? It's just an addition. I think this must be an addition now. We need to use that array. It seems a logical thing. It looks logical. But is it correct? Do not have that in it here. Yeah, of course here. So we have 5 and I need 25. So I need to add 20 and I multiply it by 5. So I need 4. And 4 is the second one. So I have 5 plus 4 times 5 is 25. So we need to make sure that we read... And I don't need this one. What the hell? That's kind of strange. Well, I need it. I need to. Yeah, I need it. Okay. Well, anyway, I think it works. Let's try it out. It's either this or that. Except that it doesn't even compile, of course. N is 1. Yeah, okay. Move that one integer type n. crash. Yeah, well, I'm close. I'm sure of it. Next failure. Well, at least that one line that goes is where it goes wrong. So P is now 2. P is 2. Oh, wait a minute. So I made it work for P is 5, and now it fails for the smaller values. It's highly annoying. Yeah, I guess so, Max. I guess so. No, don't have another profession. Failure index. I think this previous gaps thing is empty or something like that. It's just empty. Trying to read something we never use. Probably because this is already the case then. And it's 3 sums 2. This is already wrong. Could save myself by escaping this while loop before we do this, or move this to the top. Everything is equally bad. K is 0. If K is 0, then I should never get there. Oh wait, I'm getting here. I'm getting here. Yeah, that's super annoying. It doesn't really matter what I put into it then, I guess. I could just put 0 into it and then we don't crash. I must say I'm not having a super clear picture. Let's run this in the debugger. So it's for index is 1. So do the break at 90 again. Condition 1. Index is 1. Just the first time we get there, I bet. So previous is now P is 1 and just adding 1 to all integers. Sum 2 to P is 2. We set previous gaps K is 0. Don't do anything. Next failure. But K is 0, so don't do anything here. Gap is next. Print gap is 1, of course. N is 1. So now N is 2. N is next failure. Next failure is 1. Next failure is 2. Immediate failure. Okay. Yeah. Well, not really, but who cares? I think that is definitely not intended, no. How the hell is the next failure not a square here? Ah, fuck. I totally lost it. It feels now suddenly extremely weird that I'm comparing this with P itself. Well, maybe not. Frame. So we arrived at 2, and that is a failure. Well, I have to remove 2. Yeah, well, I do have to remove 2. That is true. I want to remove all even integers. So, and 2 is definitely a failure, actually. It's just, yeah, no, okay. So we add another one then. G is obviously 1, and we add it to the previous gap. So now we're having gap is 2, n goes to 3. This doesn't work. There is no next failure. The reason there is no next failure is because we're done. So why not just read one more gap? So that previous gap is 1 bigger, so I can read this. Seems like a good solution, actually. So we're reading all the gaps and read all gap values. Well, previous in advance. So, case 8. So we do this loop one more time, but it's exactly the same as the loop below. Except that Yeah. So we push back 2 here. And we did read index. Even that crashes. Trying to read index 1 here, which doesn't exist either. Because k is now this. Less than k minus 1. Well, then I'm not reading it anymore. Wait. Nope, no. You could add a test here, but hello, that would be slow. Better to just make the array one larger and then put some value into it, and who cares what it is, because you're going to escape here anyway. Yeah, I don't want to call previous next, but I do want one more value. So I just have to put something in it. No, but no crash here. This is good, this is good, this is good. The output is good. And this is wrong. So now it goes wrong for PS5. Is that not improvement? I think so. Although it feels like the same thing as last time, I must say. At some point. Yeah, back to this one, I guess. No, wait. It's the one that goes wrong is 5. Why do I not know which index it is? Index 0 was 1. Index 1 is 2. Index 2 is 3. Yeah, so it's just this one. Index 3. Break 90. Condition 1 index equals 3. Run from the start. Next, print my Sieve. Print previous, previous is 42. I'll think that's good. I'll believe the sum as well, whatever the sum is. It's 30, okay. We are working on PS5 apparently. Print PS5, yeah. Previous gaps, K is 1. reserve 1. Fuck, I'm doing it again. Okay, I'll try to remember that. 106. So we call it once. Use next. So that would be this 4 here, I think, right? We did not put a 1 into it, just put a 4 into it. Next, nothing. Add a 0. So this goes over the reserved capacity. Oops. And now we have in it 40. Previous gaps. 40. And then we do this once because and we begin reading. We not. Oh fuck! Really? Seriously? It's not even funny actually. So we begin reading 1. So that would be that 0. I think I need to start at 4 actually. So this should be I++. So gap is 4, and then we get 1 plus 4 is 5. And that is next filter, I think. Yeah. So that is always correct. And then we read the next one, which is 0. How is that even possible? So I do need a 2 here. A random number. It's seriously, it's just a random number. What are you talking about? And then, of course, we have to fix this. We start at the first value here. You know what I'm missing? Nothing, I guess. If this goes over K immediately, and it does. Does it? Actually, it does. Yeah. Maybe you should try harder to read all the gaps. Of course I should do that, I think I should do that, of course. Okay, so this is now 8. Don't do this, just read it. going to use I here, I think. And then we use plus plus I here. And then I can use here plus plus I as well. So we read a gap. This one's already wrong now. Index is 1 then. Yeah. Why is it not crashing? Anyway, I need now I need a 1 after this for this to work. So let's add a 1 anyway then. Oh, actually, I only needed. I don't care about this. It doesn't really matter. I can use that. Now we only need this if p equals 2, isn't it? 2. Index is 1. That would p equals 2. I can test the index anyway. Index equals 1. See what that brings. That looks good. I think it bloody works now. Yep. So we have actually not. No, 2 2. That should be just 1 2. No, it's not good. It's not good. But wait, we got past this one. No, it's not true. It's still index 1 that fails, because now we have 2 of them. Ugh. Okay, back to the drawing board again. Break, at least 90, still 90. Still 90, break 90. Condition, index equals 1. Run, next, previous, print previous is 1. This is 1 repeated, so that's this one. Next. K is 1. Reserve 2. Push call that once. If index is 1, yes, add another one. Okay, so now previous gaps. This is the size of 2 and contains 1 bond. We can read index 1. And then we're going to do this one once. Now we read previous gaps. So gap is just 1, of course. And n is 1. N becomes 2. And then it is equal to next failure, because next failure is equals 2. So we have to filter out all all even numbers. So we read the next gap, which is now 1. So G is also 1. So we increase gap to 2. And N is increased to 3. And then next failure shouldn't met. Oh, wait a minute. I'm using it. Of course I'm using it. I'm like, who cares what it is? But I'm using it in the next loop. Yeah. Plus the whole formula is wrong. I know, and I'm adding it, so that's actually good. But I was not sure about this one, and it's definitely not good. No, it's not good. Next failure is in the next loop. It's 4, right? It should go to 4. So that should read 2. No. So the next failure is now equal to 2, and p is obviously 2. We should go to p squared, to 4. So just adding it, yeah. So this must return 1. I'm pretty sure I put 1 into it. Fill index is 0, so we're going to read index 1 of previous gaps, yeah, which is 1. I think next failure becomes the correct value. It's 4. No. Push back gap, and gap is 2. Gaps is now a thing with a single 2 in it. And I reach the end. So now we're going into this do while loop that after that. And that calls previous next immediately. Oh, right. But this is already wrong. N is 3 and sum is 2. So we should not have entered here. The while loop must go at the top now. That's the reason. Okay, so it's just possible that we already that we just have to go through this loop here 0 times instead of once, at least once, because we do it already up here. The extra gaps here must be 1. But already, no, I read 2. How's that possible? Yeah, this 1. Okay, this will be red. Oops, no make. Now this one looks good too. Yay, we've took 2 hours, but now we have all the odd numbers. Yeah. Okay, and the next one is wrong. 7. Let's have a look at that one then. Index is 2. Finally, index is 2. I'll be happy when we are finally at index is 3. So I can Can actually look at my comments. What was that? Index is 3 or 4? I don't know. Okay, what goes wrong is this one. Index is 2. List 90, break 90, condition 1, index equals 2, right? Print previous. Previous is the repeated 2 for all the odd numbers. And then we read 1. Oh, I feel it coming. I feel it coming. Just reading 1, not doing this. Yeah, so we have only one thing here now in previous gaps. That's probably not enough. It's 100% not enough, because we always have one failure, which means that we always need 2 gaps to be able to add them. Okay, am I getting this? Not really yet. So next failure is, that's a good question. That should be the prime number. So, gap, okay, n is 1, gap is 2. Gap here, so now n is 3, so it is always failure. Now we read the next gap, we don't have that. So I don't know what's, so why is this not crashing? G is 5, really? Pretty random. It should have been 4, I think. No, it should have been 2. So it's 2 repeating, so we just have to repeat the previous value. If the size is 1, so we might as well do it like that. Index my s, if k equals 1, then push back the previous value. Just duplicate the previous value that we were at. I'm immediately going to put a breakpoint. Really, break 90, condition 1, index equals 2, run. Next. Okay, so now we have 2 2s in it. And then next failure is 2. Failure, yep. Get the next one. Calculate net, and the gap is now 4. And n becomes 5. Yeah, the next prime. So that we get next failure. The failure index now is 0, I think. Still. So we're going to read this 2 now, and then p is 3. So the next failure, we're adding 6 here. No, wait. Yeah, 6 to next failure. And the next failure was 3. Yeah, 3 plus 3 is 6. So it's just picking out all the integers divisible by 3. Skipping the ones that are also divisible by. Okay, I'm not getting it anymore, but I don't think this one will be used. Actually, it's now 6, 9. Oh, that looks good. Actually, 3 plus 6. No, of course. Yeah. I was shortly confused with 6 being 2 times 3, but it's not checking for 6. It's skipping 6. It went straight through the 9 to the 9, because 6 is divisible by 3, but also already divisible by 2, so we already skipped that one. So we tested for 3, and then the next one is 3 squared is 9. And we push back this this gap, which is 4. And then gaps is hopefully just 4. Yeah, thank God. Okay, now n is 5 and sum is 6. So we continue. And the next gap is 2. And then we get n is now 7. That's not a failure, so we push back that gap. And now we're done. Of course, now n is 7 and sum was 6, so print 1. So that one is good. So I want to set the condition to 3. Continue. So this one is now filled correctly with 4, 2. That's the first time we saw that. Case 2. All that's 2 times. And don't add anything. So now we have a size of 2 containing just 4, 2. And this fails. So we add another one to get n is 7, which is the next prime. Next failure then is 15. So we're filtering out everything that is divisible by 5. And I think it should have skipped 15 because that's also divisible by 3. So what's wrong here? Previous value was 5. It adds 10. 5 times previous gap. So that's 2 here. It should have been reading 4. Maybe I should do failure index plus plus. Apparently I should do that. 131. Yep. And that means that I don't need to add that extra index either. I wasn't sure about this one, right? I mean, we're still working on that one. Now I'm getting closer, and I think I don't need this anymore. I'm just going to bluntly remove it. Let's see what happens now. Because, come on. It's or not. Doesn't look right either. Nope. It's completely broken again. Christ. Am I mistaken about this one? I was. Okay, we have our repeating 1, repeating 2, repeating 4, 2, and this one looks actually good. It is good. 6, 4, 2, 4, 2, 4, 6, 2. That is exactly what we want. Then we get all integers that are not divisible by any prime lower than 7. It means that 49 is the first non-prime in this list. Yeah. I think it works. very good. Although just to be sure, let's compare it with my previous program. We're working on this one. I don't think it prints. Oh, it actually prints stuff. Cool. You see it. This thing has it shifted. Now the reason I was thinking that maybe it doesn't work is because I remembered that there's a 10 to 10 here. And you can shift whatever you want. Well, I'm not seeing a 10 to 10 here. Because I'm just seeing 110. That's for PS7, right? It doesn't print that, but that's a long one. What's going on here? It's not good then. This program is good. So the 1 is good to 4. As you can see, that is shifted. Here we have 4, 2. And this one is just rotated. I should say rotated. And here we have rotated once. So this 2, so this 2, and then we get the rest. I like that. Control F. So you see, so it's just rotated one position. Now you can clearly see that it's not working. It's not working. No, we have to look at index 4 because what I just highlighted here is not happening at all. It's not highlighted here at all, and we get 10 to 10 as well. So which made me suspicious. So this one, index 3 is actually working, but index 4 is not working at all. Just the first 10 is good. And then it goes wrong. But doesn't that mean that this should be wrong as well? Because this is like literally 1 plus 10 is 11 plus 2, 13 plus 4, 17. I mean, it's totally correct. It's just totally correct. These are prime numbers. It is correct. It just doesn't generate what I thought it was generating, apparently. Oh no. The point is I want to generate this, and I thought, well, it's only rotated anyway, so I might as well generate this and then find out how the rotation is. Because this seemed to be easier to generate than this. This is slow as hell to generate. I think these are the offsets. These are the. I really don't get it. Why is this 10 to 10? Yeah, I want to go to this one again. So this has my 10 to 10 in it, and that is the difference of reduced residue system for the fourth primordial number. That's the way I got it, I guess. And now we see that series, I mean, I'm having it from this 6. And I think what I generated was starting here. And the mistake that I make is that I thought that it repeats after the sum, but it's not true. It repeats after this prefix and then the sum. So this should repeat. You see what highlighted here, 6264, etc. That is repeated here. 6264, 264, 68. It just repeats. So this 10 to 10 appears again here. But the prefix is not part of that repeating pattern. And what I'm doing now is I generate this part and then a part of this part up till the point where the total sum equals the sum of the thing that actually repeats. So I'm stopping too soon. Is there nothing we can do about that? Well, first I have to check that that is the case. So we have ten to 42, 10 to 42, 4626, 4626, 4 to 4662. 424662, but it's already in it. I think what I generated is correct, but I'm not continuing long enough. On the other hand, there's a lot of repeating going on here. The previous one, just literally repeated over and over and over. It probably has to do with the same mistake. Oh. I'm not seeing this 8, for example. Even if it is this, right? So I could just highlight this whole thing here, I guess. All the way up till that 6. Let's copy it. Put that in here. Oh, nope. It's already not highlighted. It's going up a lot. Let's start deleting stuff. Nothing. No. Oh, I'm having commas here, and I don't have commas here. I do have an 8 here. That was a while ago. I don't have an 8 here. Do I used to have something that worked a while ago and now it doesn't anymore? What, when? When? Now I'm curious. Was that before I started the stream? Yeah, this is like, I don't know what this is, but no, it's not it. Go down. This is it. Fast prime 4. I was already streaming here. I think that this is before the optimization then. At some point I had it working, so that would be this one. And then I started to do an optimization that, yeah, with the NS. And after that it broke and it never works again. Because it's still not producing that output. That is this one here. You know, I'm going to delete stuff until I see when it, fuck. Well, that is it already. No. No. I just jumped up again. I need this one to match. Index 4. Okay. This one is right. This one is not right. I'm going to look at index 4. And at least here we have then the output that should be produced. So let's copy that. Okay, let's just prefix plus the part that starts repeating. Yay, my comments, my comment k equals 8 is now working. So this would be reading it 8 times, and then we get, of course, this thing here. But also what is in the comment somewhere. Let me look at the comments. Can we go back like this? I think so. Yeah, this. 642, so just a 6 in the beginning and a 6 at the end, and then a 2. And that already worked, so. No, next failure is the first one, so that would be 7. So 1 plus this 6 here. We already have the 1. So we're going to read I is 0, the previous gap, first one is 6, gap is 6, n becomes 7, so this is a failure. Which means that we add the next gap to it, which is 4. Making the total gap 10, making n 11. And that would be the first 10 here. So this 10 might as well peek here, of course. So the 10 is correct. The next failure, the next failure is going to be the next integer not divisible by, but divisible by p. So the current failure is p itself. And that means that the next failure is always the square of p, right? Because any smaller number that's divisible by 7 is has a factor that is smaller than 7. So I need to add 42, sorry. We need to go to 49. So we need to add 6 times 7, and of course the first gap is 6, so this should work. Next value is now 49. Now we push back to 10. And then we go to the next k. So the next gap was 2. And we add that to the 11 to get 13, of course, and then that's not the next value. So push back, we just copy all the gaps that we read. So this was 2. That would be this 2, and we're going to read next 4, 2, 4, 6, 2, 6, and so on from previous gaps. So actually I might as well do that. We're going to read 42462. 42462. And then we begin at the beginning again. 2, 6, 4, 2. There's done something that's different. 6, 4, 2, and then this gets combined into that 6 here. So we read a gap, we push it back, we read a gap. In the meantime, n has become 23, so we push it back, we read it. Push back, we read the next gap. Do 1, push it back, read a gap. Push it back. What the hell happened? We stop. No, we still don't stop. That's just, I'm an idiot. Next, push back. Next, how much is in? Almost there. Push back. 47. Push back. Read the next gap. Now n is 49. So what we pushed back so far to gaps is 10, 24, 246, 26424. 10, 24, 246, 26424. Yep, and this 6 was the first one that was going to be a short circuit. So that happens right now. This is the failure, we re-key G, and then we make gap 6. And we skip 49, go to 53. And then the next failure is yeah, I guess it just works. Huh? Next failure is now 63. 63 divided by 7 is 9. No. Absolutely not. Why? What? No. You have to go around, fill in. No, that's not true. Previous gaps is big. No. No, it's still there. 0, 1, 2 is 2. We just read the 2, so I just added 14. Is that true? Fill the index 2, 0, 1, 2. This is 2 times 7 is 14 was added. Yeah, we had 49. So we had 7 times 7. And now the next one is 7 times 11, 77. We should have jumped to 77. I mean, 7, next prime after 7 is 11, so yep. $77 minus 49, 28. 28 divided by 7 is 4. We should have been reading a gap of 4. And we read 2. What the hell? I'm so not getting this. Still not correct. What is 7 plus? Right. So I just moved this plus to the end. Code duplication. I forgot that you did there as well. I think we're getting there now. I have a good feeling about this. At least. Okay, where's my 10 to 10 now? It's hidden. There's a 10 to rotate to the beginning 10. But. Anyway, does this now compare to that or not? Yes, it does. Why did I stop here with the highlight? So it must be 210. Yeah, 7 times 30. There's a lot more to compare, yeah. And then is it actually rotated? That means that this thing already repeats. I just didn't see it. No formulas here. Ten, 2, 4, 2. I have only one mouse, but I have a finger. 2, 4, 6, 2, 6, 4, 2, 4, 6, 6, 2, and so on. Yep, it does repeat from the beginning. Thank God. And I thought I had copied everything up till here. But apparently I don't, and if it repeats, I just have to copy it all the way up till there. That would be the repeating stuff, right? Here after this it repeats. Yeah, so let's copy this one. Which is way more. Yes, we got all of them. Correctly. That was way too long and too much work for getting this correct again. With just a minor change, more or less. Getting rid of the modulo. Okay, the count doesn't help me anything. I want to get rid of the count. Or not yet, I don't know. Well, there was a speed up in the way, in the sense that I kind of know what is coming after when I'm reached halfway. So what you could do is just see when the n does go over half the sum, then basically we already have the exact points where it goes wrong without even doing a compare. So I could just make a loop that copies, which eventually would speed things up, I think, for the very, very large case. But speed things up, it does mean that we need to store all those values. That's of course, yeah, making things super slow as well, probably. Might as well just continue with the test on next value, I think, maybe. Yeah. I mean, for half of the loop, I could get rid of testing next value, but that would mean that for the first half of the loop, I have to store all the syntax, which is probably even slower than doing the test. It's like a lot of cache misses, but storing. Let's not try to make it that fast. I'm happy with this, I think. And that means I'm not interested anymore in the count. Remove that. Just do it like that. Now this code looks a lot alike, except that I'm calling previous next here, and we're calling previous gaps here. Wouldn't it be faster if I just got rid of that code at the top? I mean, it's like the same thing, except previous gaps previous next. This, that. I have the feeling that I can just reset it again and then not do this. Let's comment this out and do a previous reset. Yeah, looks good. Okay. Where's my highlight? There it is. So it's still good. It's not super clear actually, but I think that it might be faster to use the same executable, the same assembly for the execution. That's also some cache stuff. So we do read now from two different memory parts. We read from this array, and we read from the array in previous. Yeah, on the other hand, k is pretty small, I think. compared to the whole thing in the end. It's also a bit vague. So I think I'll just do this because it's not clearly slower, not at all clearly, maybe even faster. And I definitely get rid of code duplication. Code duplication is bad, as you just saw. Because that plus change already got lost. Did go wrong, I meant, because I copied it. Now this reset here belongs to calling next. So I'm going to put that right in front of the loop there. Put a new line here, of an empty line here, because the comment refers not to just this part, but also the next. And I want this empty line here for some reason. And I'll reset it again here. Because start anew. Now, did I break it by adding new lines, or is this thing still working? It still works, okay. Yeah, this is good, because I don't have my module now. I like that, no module. Now there's another speed up that is absolutely necessary. Namely, calculating way too much if you want to go to a certain point. Let's say I want to calculate all primes till 100 to keep it easy. To begin easy. You think of the sieve of Eratosthenes, then you only need to do the square root of 100, so all the primes up till, well, up till and including 7. So just 2, 3, 5, and 7. That's the only ones that you need to fill the sieve with. And then you're done. You have all the primes till 100. And here we are doing all the work that is might be necessary to go to infinity. But if you already know that you're going to stop at I don't know, a trillion or something like that, then it's not necessary, right? So in this case, the question is, well, what can I do to? When can I stop with what, or what can I reduce? Now, especially these things become those gaps arrays becoming enormously big, very quickly. I wonder if I'm even reading that. Let's say I want to go to 100 primes till 100. Then I think I need to go up till prime number 7, like I said, which is index 4. No, that doesn't. That only gives me 5. I need one more apparently. I already break out of it. Yeah, so that's larger than 4 then. So 5. Okay. And yeah, now you see all those prime numbers, right? It's 2, 3, 5, 7. Oh, here we go. 11, 13, all of them till 101. So that's enough. And that looks like, oh, that's going to be nice, but it's not, because if I make it even bigger, then this array is going to grow out of bounds anyway. It's already overshooting it by a bit, but hell. The next one is 11 times lush. So, and the next prime is definitely not the square root of 11 large. So something is going horribly wrong. Let's say we want to need 11 as well, so let's just do all prime numbers till 200, okay, instead of 100. All primes till 200. What's square root coming up? Square root is, I don't know, and I'm sitting in the dark, so I can't see my calculator. Oh, and I have to eat. Oh. Ah. Calculator. Sorry, I need to put something in a microwave. Otherwise, I'm not eating. It's not good. So 700 watts, 5 minutes. Yeah. So in 5 minutes I start eating, and then I cannot stream because I'm eating. I mean, that sounds really stuff like that. I'm going to watch a movie then. Probably have to go just one larger anyway. Oh, so yeah, square root of 200. It's 14 something. Well, I could have known that. Yeah, okay. 2 times the square root of 2. 10 times square root of 2. 14 point something. Yeah. So we need primes up till and including 13. Oh, that's a lot. It's not even, this is not even enough then, right? This was up till and 7. 7, 11, and we need 13 as well now. So, yeah. 2, 3, 5, 7, 11, 13. 17, 19, 23, all the way up till 200. But in the meantime, we also generated this ridiculous array with 5,760 elements. Why? Could we have stopped? Could we have stopped way sooner with this array? Yes, of course we could. These are just not prime numbers. Well, they are prime numbers up till and including this one, not that one. Not this one, because that one is the square of the prime that we're filtering out. So 13 here. So that is 13 squared. Everything before that is not divisible by any prime lower than 13, and therefore they must be primes themselves. Well, they're not divisible by it, but then just by themselves. Well, no, actually not, because you stop here. None of them is divisible by 13, except this one, but also not by 11 or 7 or 5 or 3 or 2. Which is exactly what you need to go to 13 squared. 13 squared is needed to go larger than 200. Or is it? 11 squared was also enough. That is, I think, no, of course not. 11 squared is not 200, it's 121. This is not 13 squared. That's 13 squared, so 169. What the hell is 289 then? Oh, 17 squared. It's the next prime number. So this prime number squared. Oh yeah, right. Excusez-moi. Sorry for the confusion. Would ChatGPT say. Oh, you can hear the beep. That means I'm going to eat and watch a movie. And after that, I might continue with this. Still wondering though, when can we stop with this? When can we stop with the generation of? I think this 16 here means just 17. I think we can just stop as soon as we reach whatever we need to reach. AKA 199. Which is, well, eight elements. So, well, I don't know, just that, for example. The rest is irrelevant and easy to detect that it is irrelevant. But what about this one? It's also big, of course. It should also be able to stop sooner here. Till which one do I still need this? Also till 200? Which is more than what I print here. The sum is 2310. So we go to 200, so that's just a fraction of it. This one has a sum of 210. So here, this is we probably need all of those, almost all of those, not even exactly all of them. You can remove the last two. This 10 is maybe necessary because then you're not, well, yeah. I think the 10 is just necessary. Well, basically, you just have to generate all of this, and then maybe something like that. And then here, maybe something like that. And the rest is not necessary. I mean, you're still able to generate all prime numbers till 200. I think it's not faster than the Sieve Eratosthenes. It's just more complex. It's more fun, actually. I think it's more fun. Yeah, I can't think of it. I'll have to think about it again. I think, like, offline, how to continue this. I'll show the fast primes 3 quickly. And this is slow, in my opinion. And the worst part is it gets slower and slower until it goes like a crawl and overflows. What the hell? Number of gaps. Well, this still works here. You can check it. So you can just, there's a site, you can ask it. Maybe we can show that even. There's a site here. Where is that site? No, this one. No, this one. Yep. Go back. No. I don't know, man. It's 1,000 primes. It's not what I wanted to see. No. Well, there's a site that you can just type in. What is the nth prime number? You type in this number and you'll see that that is the prime number. So it's proof that it is correct. But yeah. I'm going to watch a movie. I'll be back another time, I guess. Thank you for watching.